Diffraction. Diffraction is the spreading of waves through an aperture around an obstacle corner. The Huygens wave theory of light helps to explain that by stating that every single point of a wavefront behaves as secondary sources emitting wavelets in phase with one another. In doing so, diffraction occurs. Let's try and take a look by looking at the three circumstances. When the slit wave is much bigger than the wavelength, the wavefront can pass through and there's no diffraction. However, when the slit wave is comparable to the wavelength, the light that can enter here will act as a secondary source, emitting light waves to these 3 points. And these 3 points could then spread to more points, thereby causing diffraction. And when the slit separation, when the slit wave is smaller than that of the wavelength, light rays are being diffracted and they are being bent. We will now explain the diffraction of single slit. Then after that, we'll move on to the double slit. In the single slit, what we have in the diagram down here is that this is actually firstly the slit wave. Then from the slit wave itself, we can actually have 2 point source that is directed to one point whereby you get your first minima, meaning to say that at this point you get destructive interference. The reason for having this model is that if this were to achieve a destructive interference, then the same 2 sources could be replicated to give a destructive interference. So from there, we know that the distance traveled by this source is from the distance from here to here, and the distance traveled by this source is from here to here. So if we were to magnify this triangle here to this length here will now becomes the path difference. So will becomes the path difference from the source here to the first minima, and this source here to the first minima as well. So this now will become the path difference. So the path difference is now L, and because this is a right angle triangle, so this length L is actually A over 2 sine theta. So therefore, it's multiple of half wavelength because that's for destructive interference. So the 2 and 2 cancel away. So that's how we end up with the formula that sine theta equal to n lambda over A for all the minima that you can find inside for a single slit diffraction. And in terms of the intensity itself, here will be 0. So this will be what we term as a central maxima. So this will be pretty bright. And then again, you have another first minima here. So these two are always mirror image of each other. Now let us take a look at the double slit. In the double slit, you have now 2 point source. In the same vein, they will now go to one spot, but in this case now, it is the first maxima, which means constructive interference has occurred. So similarly, we will be zooming into this triangle, and by studying this triangle itself, this is actually the slit separation. It's no longer the slit width, but it's the distance between the 2 slits. Okay, it's the distance between the 2 slits. So in this case, L will also be the path difference. So the path difference remains as L, and L in this case now, geometrically, it is actually d sine theta. So for constructive interference, because they are all maxima, the path difference of d sine theta must now be equal to multiples of your wavelength n lambda. That's the reason why for double slits, the formula is sine theta equal to n lambda over d, while d is the slit separation. For the case of single slit, the minima occurs when sine theta equal to n lambda over A, and A is actually the slit width. Finally, in both instances, we have actually got D as the distance from the slit to actually the screen, slit to the screen. So in this case, from the central maxima to the first minima, we label them as the distance xn. So tangent theta is now xn divided by d. So if theta is small, sine theta is approximated as theta, which is equal to xn over d. And we could now have sine theta. If theta is small, sine theta is also approximated as theta, which is equal to n lambda over A. So in this case, we will have this as the formula. So that's the reason why we can say that the fringe separation is actually, so from here, we know that xn is equal to n lambda d over A, which means it's 1 lambda d over A, 2, and so on and so forth. So it means the fringe separation the fringe separation between the minima is actually lambda d over A. Let's now take a look at the double slit. For the double slit, in the same vein, sine theta is approximated by theta, which is now equal to n lambda over d. So xn, which is actually equal to xn over d. So in the same vein, we're using this expression to place down here. So xn now is actually n lambda d over d. So in this case, the fringe separation is lambda d over d. All right. So this is the two expression that allows you to find the fringe separation between the minima. While this is a fringe separation that you can find, well, this is actually the fringe separation between the maxima. This dotted line here depicts the intensity. This dotted line here depicts the intensity of the fringes. So in this case, this is the first maxima. The central maxima will be the brightest in terms of fringe. And then after that, you have another first maxima here, which is actually mirror image. Fairly similar to the case of the single slit, but in the single slit, you are actually rather looking at the minima. Finally, we can also use this formula to calculate how many of the minima can we have in the single slit diffraction. In this case, the formula to use rather is that sine theta must be less than or equal to 1. So therefore, because of this, because sine theta is equal to n lambda over A, so that's less than or equal to 1. So n in this case must be less than equal to A over lambda. All right. So if you do a calculations, and for example, you end up as calculating this value as 3.33. All right, 3.33. And therefore, the number of minima that you will have will be 3 on the top and 3 below. So total, based on these calculations, there will be 6 minima. For the case of the double slit, we'll be looking more at the maxima. So let us take a look. So in this case, sine theta similarly must be less than or equal to 1, which means n lambda over d is less than or equal to 1. So in the same vein, n is less than or equal to d over lambda. If again you calculate your value as 3.33, then you need to bear in mind for the number of maxima here, all right? Because n is less than or equal to 3.33, so there are actually 3 maxima on the top, 3 maxima below, and not to forget you have 1 central maximum here. So therefore, total it will be 7, because it will be 3 times 2 plus 1, which is actually the central maximum. Okay, let us now take a look at the intensity versus the angular position graphs. This is actually the diffraction pattern that you will observe for a double slit. So in this double slit example that we have the fringe, we have the slit separation D, and each of these slit down here has a slit width A. So based on the maxima that one will observe for double slit experiment, for diffraction of double slit, you'll realize that this is the first maxima, second maxima, and third maxima. And it seems that the fourth maxima is missing in terms of its bright fringe. So based on the fourth maxima itself, this will be the formula that you could use for your calculations, and the angle theta 4 will actually be this. The reason why the fourth maxima is missing, because for the double slit, each slit itself will actually has its minima. And it has its minima governed by this equation here, governed by the equation of a single slit, where the first minima will occur when sine theta is equal to n lambda over A in this case. So the first minima will occur when n is 1. So based on these calculations, when the delta 0 coincides exactly with the fourth maxima of the diffraction pattern, you will have a missing peak.